Okay, thank you very much for being here, all of you. We have the extreme honor and pleasure to welcome tonight Kevin Oregan. So he has been the director of the Laboratory of Psychology of Perception in University Paris-Descartes. His specialty is about consciousness, in the sense of, I will take the title of your book, why doesn't red sound like a bell? Actually, how does the feel of consciousness can be understood? And so Kevin is going to tell us about this in the framework of a theory he has developed called the sensorimotor theory. Now I'm going to leave you the deck, and up to you now.
Thank you, Jean-Christophe. A clipping from the Daily Mail. Now, the first robot able to feel emotions and form bonds with humans that look after it. Now, do you really believe this? You're laughing. You should know. You build the now. But you seem to doubt. In fact, the author of this article in the Daily Mail also doubts. He actually says, now has been designed to mimic the emotional skills of a one-year-old. Probably very few people believe that a robot will ever be able to have the emotions of a human. Most people are wrong. There is nothing to stop robots from having real feels. That's what I'm going to try and convince you. Let's see why most people think there's a problem. Let's try and see how most people would go about making a robot that really feels something. For example, how would we build pain into a robot so that it really hurt the robot? For inspiration to solve the problem, let's look at how pain occurs in humans. You touch your finger to the burning fire, information goes up the afferent pathway up into the integrating center in the spinal cord, and then after a few synapses, it's sent back down to the muscle, and your finger jerks off the heat. Now, of course, that is just an action-reaction loop. That doesn't give us the pain, does it? You could easily build this into the robot, but would that make it hurt? Obviously not. Something more is needed. And undoubtedly, that's why the information has to go up to the brain. So let's look in the brain and see what the secret is that generates the actual hurt. These are the brain centers involved in pain sensation. There's complicated circuitry here. There are many brain centers involved, connected in complex ways. Furthermore, there are chemical pathways involving neurotransmitters, such as serotonin and norepinephrine. But all this is just chemical circuitry or electrical circuitry. How could chemical or electrical circuitry, in fact, how could any physico-chemical mechanism give rise to the hurt of pain? There seems to be a fundamental problem here in creating the hurt of pain. Let's leave pain aside for the moment and look at perhaps a more basic question. Color. What makes us feel colors the way they are? What makes red feel red rather than green? Let's look in the visual system and see whether we can find the answer. We know that in the retina, there are three types of photoreceptors called cones, L, M, and S, sensitive to long, medium, and short wavelength bands of light. And these are packed densely on the retina. That's what gives color sensation. Higher up in the visual system, these three color signals are recombined in different ways to give two color channels and one luminance channel. The color channel gives you a signal that's proportional to the equilibrium between red and green, and a signal that's proportional to the equilibrium between blue and yellow. Now, thinking about it this way, you would expect that if you wanted to get a pure sensation of red, well, what would you do? You would expect a pure sensation of red would occur when the red-green channel is maximally activated in the red direction. And the blue-yellow channel should be activated in the neutral position. There should be no activation. Unfortunately, that's not what happens. In order to see pure, unique red, it turns out you've got to add some excitation in the blue-yellow channel. So something is wrong. Furthermore, to feel that you're seeing a unique blue, which contains no green or red, only blue, it turns out you've got to have some green activation, in fact. Unique blue is not given by just activation in the blue-yellow channel. Something is wrong. Well, let's go look up in the brain and see higher up in the brain. Maybe there's the answer. The retina is down here. There's a lot of complex circuitry going on in the rest of the brain. These are all the different sub-areas in what's known about the visual cortex. V4 is the area which people usually think is mainly concerned with color perception. Now clearly V4 will be activated in one way when you see red and another way when you see green. Now what is it about the activation in V4 that gives you that red sensation rather than the green sensation? Could it be something about the frequency of oscillations? Something about the connectivity, the reverberations? Could it be something to do with the neurotransmitters that are different between red and green? If it was any of those things, you could ask, well, what is it about the neurotransmitter that gives red, that makes it give red rather than green? And if you said it was in the nitrogen atom in that neurotransmitter, then I could say to you, well, what is it about the nitrogen atom that gives you red rather than green? There's an infinite regress of questions. Whatever mechanism you propose or find in the brain that's going to give you the answer, I can always ask you, what is it about that mechanism that gives you red, not green? There's a fundamental problem here in understanding what gives the redness of red. In fact, there's an even deeper problem, and that's the problem of sensory presence. Consider the feeling of redness. It feels like something to you. It doesn't feel like nothing. But if you think about redness, then there's no feel. It has no sensory presence. What is it about the brain areas concerned with thinking that doesn't give you that sensory presence that you have when you have sensory feel? Or the other way around, what is it about the sensory areas that give you that sensory presence that you don't have, with thinking? And look at autonomic functions in the nervous system, like the sensory circuits that control the degree of glucose in your blood, or oxygen in your blood, or the chemical metabolism in your liver, for example. These are complex sensory systems, and yet you don't feel them. They have no sensory presence like the redness of red. And yet they're big areas in the brain that are dealing with this. What is it about the areas dealing with red that gives you that sensory presence that is not there in the areas to do with blood glucose concentration? And if you give me an answer, and you say, well, it's the neurotransmitters, or the connectivity, or something about the quantum gravity effects in the microtubules, which is one thing that's actually been proposed, I will ask, well, what is it about those quantum gravity effects that gives you the feel of red? And there's the infinite regress of questions. There's a fundamental problem. And that is why people think that robots will never feel, because they've got themselves into a way of thinking that leads to these problems. And the problem is called by the philosopher the explanatory gap. There seems to be no way of explaining feel in terms of physico-chemical mechanisms known to man. There's no way of making the link between physics and experience. I've given you the example of color, no way of making the link with physiology. I've given you the example of sensory presence. There's no way of making the link with physiology. There's no common language. That's the explanatory gap. What I think is that this is a big confusion. It's to do with the way we're thinking that's gone wrong. Let's think back to what happened at the beginning of the 20th century with regard to the problem of life. People were having similar problems with regard to the problem of life. There were the vitalists who thought that life was something special that was imbued into organic systems by a so-called élan vital, or vital spirit. Today we know that that was the wrong way of thinking about life. Life is not the kind of thing that is generated by certain organic systems. Life is simply a word that describes the way certain systems interact with their environment. Maybe we could make progress with the problem of feel and consciousness by taking a similar stance with regard to that. Supposing we thought about feel in a new way, and we thought that the quality of the feel is not something generated by special brain mechanisms. Let's imagine that the quality of a feel is just a word. It's a word that describes the way we interact with the environment. Now that doesn't make much sense, of course, at first. But let me give you an analogy, which maybe does make more sense. Oh, sorry. So I'm suggesting we take this view. The standard view says brain creates feel. The sensorimotor view, as I call it, proposes that feel is a way of interacting with the environment. But that doesn't make much sense at first. Let me give you this analogy. Consider a sponge. You feel the sponge, it's soft. Where is the softness of the sponge generated? That's a stupid question. Softness is not generated at all. Softness is a word that describes how soft things behave when you press on them. They squish. Softness is a sensorimotor law. It's a law that describes the relation between your actions and the sensory input that you get when you do those actions. Now that makes sense with softness. But can we extend this idea to all sensations, to red, to pain, to the taste of onion? That is the bet of the sensorimotor theory. So let's see if we can make this work for color. Remember, I asked you, how do you explain the fact that pure red, unique red, is not created by activation of the red-green channel in the red direction, but requires a bit of yellow? Can we explain that using the sensorimotor approach? Yes, we can. I'm going to show you how to do it. But first, we need to think about redness and color in general, not in terms of activation of neural networks, but in terms of things we do. Now it seems odd. You look at a light, there's nothing you do. You don't have to do anything to see the redness of the light, is there? But there is a way of thinking about it. Think not in terms of lights. Think in terms of surfaces. Take a red piece of paper. Move it around under different lights. The light coming into your eye depends on the way the surface is being illuminated. If it's illuminated by the yellow sunlight, the light coming into the eye will be more yellowish. If it's illuminated by the blue skylight, the light will be more bluish. Redness is not the light coming into your eye. When you look at a red surface, the light coming into your eye is not red. Because if you look at a red surface in a room which is only illuminated by blue light, the only light coming into your eye is blue, and yet you see the surface as red. So what is red? Red is not the light coming into your eye. Red is a law that describes how surfaces change the incoming light. What is absorbed, what is reflected. That law is what describes color and characterizes color. Red is the way red things change the light. It's not the color of incoming light. So let's see how we can make a mathematical model of this sensorimotor approach to color. And it turns out to be very easy. As I said, color is sensed by these three photoreceptor types, L, M, and S cones. If you look directly at the illuminant, you will get a certain amount of activation in the L, M, and S cones that can be described as a point in a three-dimensional LMS space. The light lands on the surface and is reflected. Some of the light is absorbed, some of it is reflected. And if you look directly at the reflected light now and measure the amount of activation in L, M, and S cones, you now have another point in the LMS space. So a color is a law that describes how incoming light in the LMS space is transformed to outgoing light in the LMS space. And it turns out that the law can be very accurately described by a 3x3 matrix. It's a consequence of the linearity of the physics of the situation. So I can go through colors, and I can actually calculate mathematically from first principles using databases that I find on the internet, for example, about the reflectances of these surfaces. I can calculate the 3x3 matrix for each of those surfaces. So that's what we did. And what did we find? Well, there are lots of numbers, obviously, but we looked carefully at those surfaces, at those matrices, and we found something interesting. Among all those matrices, there were some which had the property of being singular. Now, you as engineers know that a singular matrix has the property that it'll take a point in a three-dimensional space and project it down into a lower dimensional subspace. So essentially, a singular matrix is a simpler law than usual. So let's look at which are the singular matrices among these colors. Here is a graph of the singularity index that we plotted for each of the surfaces that we have in the ground plane here. And you see, interestingly, that some of these surfaces have the property that they're highly singular. And those highly singular surfaces are exactly the red, yellow, green, and blue surfaces. Now that's interesting, because color, after all, is a symmetrical thing. There's nothing in the wavelengths of light coming in to single out particular colors. But we all know that there are things that we call primary colors. Why are there primary colors, given that in the electromagnetic spectrum there's no asymmetry to create such primary colors? Here we're looking at something about surfaces that suggests there is an asymmetry here due to the way the brain interacts with surfaces. Furthermore, this graph reminds us of something. In the 1970s, two anthropologists, Berlin and Kay, went around the world asking people, they showed them these chips of color and asked them if they had names for them. And they went through more than 100 non-industrial cultures throughout the world. And what they found is that some of the surfaces people had names for, and some of them they didn't. And the surfaces that people had names for are plotted here in this graph. The surface that people had the highest chance of giving a name to was, guess what? Red. And then there was yellow, green, and blue. They were exactly the same surfaces as predicted by the sensorimotor theory. This is an incredible victory for philosophy, because a simple philosophical idea has made an empirical prediction and has confirmed through the anthropological data that simple laws of interaction with colors are those that people are going to retain when they give names to surfaces. The two graphs correspond almost exactly to within one chip. Well, what about the question I asked at the beginning? It turns out that you can actually also predict the data for this. Let's look at the actual psychophysical data concerning what colors people consider to be unique colors. So here are some data concerning what colors people judge to be unique. And on the y-axis, you have what has been calculated as the equilibrium in the blue-yellow channel, known to exist in the visual system. On the x-axis, you have the equilibrium between the green-red channel. The dots in this graph are the colors, are the excitations in these channels that are known to produce unique hues, unique colors, colors that are considered to be pure in the sense that I was describing. So these dots here correspond to people who have judged that if you excite the channels in these ways, this color is seen to be unique red. And these are unique blue, unique green, and unique yellow. And as I told you before, unique red needs a bit of activation in the yellow channel in order to appear unique. And that's why these dots are sloping downwards. You need some activation down in the yellow direction in order to see the red as being unique. And the same is true for blue, yellow, and green, which are not vertical and horizontally displayed, but they're off the vertical and horizontal, which is contrary to the prediction that the neurophysiologists would make. But look at the black lines. The black lines are the predictions of the sensorimotor theory. They are exactly on the data, with no parameter adjustments whatsoever. Pure philosophy has given exact empirical predictions. Another victory for philosophy. So I've shown you how the sensorimotor approach, a simple philosophical idea, has enabled us to make interesting predictions that were confirmed as regards color. I want to go on now to talk about the question of sensory presence. So remember, sensory presence is the fact that sensory feels like red or the taste of an onion or the sound of a bell have this sensory presence as opposed to thoughts and autonomic functions in the nervous system, which have not such a strong sensory presence. With the sensorimotor theory, in order to explain this, we have to explain it in terms of sensorimotor laws of interaction with the world. So we have to look at the laws that describe what we're doing when we're seeing red or tasting an onion that are different and explain this sensory presence compared to the laws that govern our interaction with the world when we're thinking or when autonomic processes are going on in the nervous system. And I don't have time to go into the details, but if you look at the laws that are obeyed when you're actually interacting with the world and sensing something with your 5 classical sense modalities, hearing, seeing, tasting, smelling, and touching, then it turns out that there are 3 laws that obtain for those sensory systems, and I call them bodiliness, insubordinateness, and grabbiness. I don't have time to go into the details. Let me just look at grabbiness. Grabbiness is the fact that sensory channels can incontrovertibly capture attention. So if I make a big noise, your attention will be immediately attracted to the noise. If there's a flash of light or a pungent smell, your attention cannot but be attracted to this sudden change. Okay? So here's an example in vision. You see here that there's a change occurring in the picture. You have no doubt that when you look at a picture like this, you see everything in the picture. And the proof that you really are seeing everything is the fact that if anything should change, well, it pops out and you can see it. This is the grabbiness of the visual system that lets you believe that you are seeing everything in the picture. But it's possible to remove the grabbiness. Here, I'm making a change in the picture by changing the picture so slowly that the grabbiness of the visual system is not being excited. And so your attention is no longer attracted to it. So you're looking at this picture. You think you see it all. But I have proof that you do not see all of the picture. You only see the bits that you are attending to and the features of it that you're attending to. Because what you see now is quite different from what was there a few seconds ago. It's been changing very slowly, so your attention has not been grabbed by it. I don't know if you've noticed the change. I'll go back to the initial picture. There. So you see almost a third of the area of the picture changed without your seeing it. So this is a phenomenon called change blindness, which was a prediction of the sensorimotor theory, which was confirmed in my work with Ron Rensink on change blindness. And there are different ways of doing change blindness. Change blindness has now a big literature in psychology. So change blindness is an example showing the importance of grabbiness in creating the impression of seeing. We don't see everything around us. Seeing is a sort of illusion, and it's maintained by the grabbiness of the visual system, which gives us this feeling of visual presence. The visual presence is partly due to the grabbiness that occurs when we have sudden changes that attract our attention. Actually, we don't see everything in front of us. There is no internal replica of the outside world, which is somehow active in order for us to see. We only see at any moment what we are currently somehow cognitively manipulating. That's the idea. So that was another prediction of the sensorimotor approach. So I'm not going to have time to go on to 2 other predictions of the approach, sensory substitution and the rubber hand illusion. You can go and look in the literature on that. I want to talk about space. So think of the brain sitting inside the dark cavity there. It has no idea what's outside of it. It has neural inputs, it has sensory inputs, it has motor outputs going out. Let's say at time t equals 0, we have millions of nerves that are firing and that are giving you inputs, and these, say, would be the activation of all those nerves, 13, 21, 242. This is the activation happening at time t equals 0. And a fraction of a second later, t equals 1, the neural input has changed to this. And now maybe you've made an action, and now the neural input has changed to this. That is all the brain knows. It doesn't know that there's space out there. It doesn't know it has that there's a body attached to this brain. A priori, the brain knows nothing. How within this mess can it understand that there is a body attached to the brain, that body is immersed in a thing that we call space, a kind of vessel or medium in which it can move and in which other objects can move? How can this be found within these numbers? And how can it be deduced without knowing a priori that it's there? Consider evolution. Evolution has created brains that solve this problem. But presumably, a priori, there was no reason for evolution to know in advance. So how did evolution solve this problem, if it was evolution? Or if it's not evolution, how does the brain of a child, as it comes out of the womb, realize that this brain is attached to a body and the body is immersed in space and that space has the properties that it has? It has 3 dimensions, etc. The answer, I think, lies in sensorimotor contingencies, sensorimotor laws, the laws that govern the way my actions change my sensory input. And so I don't have time to go into the details, but with a postdoc collaborator, Alexander Terekov, we have looked at a way in which a brain, which has no a priori knowledge whatsoever, connected to the outside world and to its own body, can deduce the fact that its body is immersed in space, and it can deduce the fact that space has certain properties. It is a thing that we could conceive of as being a vessel in which the body moves and in which objects move. And to discover this, all we need to do is to use one idea, which is coincidence detection. Now, I can't really go into the details. The idea is that we have an algorithm. The algorithm studies the sensorimotor relations, that is to say, the relation between input and output. The agent, it could be an animal or a robot, makes random actions. Sometimes the environment moves. When the environment moves, let's say this is the environment here, a circle of light sources. The environment can move either making a non-rigid deformation, or the environment can move and make a rigid translation, for example. It can have different kinds of changes in the environment. And what the algorithm does is it registers cases where sensory input is the same. So it detects coincidences in its sensory input. And then it makes a map between corresponding values in the motor output or in the proprioceptive values. And it creates what we call a function phi. This function phi is a map from proprioceptive space to proprioceptive space, or we could say it in another way, from motor space to motor space, that links cases where you have the same sensory input at a given moment. And it turns out, and Helmholtz and Poincaré had pointed this out back at the end of the 19th century, that such cases correspond to rigid displacements of the agent within the environment, or of the environment itself. So to test that this works, I can't go into the details of the algorithm because I don't have time, but let me just show you the results of a simulation we did. This is a simulation we did. We tried to make a fairly complex, randomly constructed agent, but for problems with computer the calculation time, we had to limit its complexity to a certain extent. So we chose a 2-dimensional agent. Of course, the brain did not know anything. It did not know it was 2-dimensional. But the agent itself was a 2-dimensional thing. It had a body, which is sort of like a tray that moved around in a 2-dimensional way. It could shift from place to place on a surface. And inside this tray, it had a retina. It's like my eye that moves within my head. This agent has an eye that moves within its body. And it lives in an environment which is a 2-dimensional environment of light sources. Now this is completely arbitrary. It could be sound sources, it could be echolocation, it could be whatever you like. There's no limitation. It just has to be continuous functions, okay? And the agent has proprioception, or equivalently motor commands, which also just have to be continuous functions that modify the position of the retina within the body. But this can be completely complicated, nonlinear, whatever you like. Okay, there's no restraint on that. It can be And this we're trying to simulate animals or robots, whatever you like. And we get the agent to move around randomly, and it looks at changes in its environment, and it calculates these coincidences, and then it calculates these so-called phi functions, and then it uses these phi functions to estimate changes, to classify changes that occur in its environment. And so what we want to do now is to check whether with these phi functions, the agent has some understanding of what is meant by space. So to check, we can't ask the agent, so we get the agent to do some tasks which are going to check whether the agent understands spatial notions. So it's like getting the agent to do a Turing test. And we want the agent to be like a subject in a psychophysical experiment. We ask the agent questions requiring what we think kind of instantiates spatial knowledge. It instantiates the notion of space as a vessel. So we've got 3 tests. The first test is we ask to see if the agent can discriminate its own motion from environmental changes. So we get the agent to move, and at the moment that the agent moves, we have the environment either at the same time make a non-rigid deformation, or we just let the environment shift as it would if the agent shifts rigidly. And we check to see to what extent the agent is able to discriminate these things using the phi function. And here's the results. The percentage of deformation is shown on the x-axis, and the size of the amplitude of the jump that's made by the agent or the environment is on the y-axis. And you see that here this dark area shows a probability near 1 of the agent correctly judging that there has been a rigid displacement and discriminating, therefore, changes that are due to its own motion from changes that are due to environmental changes. So that is a first very important thing that any agent must be able to understand if it is to understand the notion of space, that when it moves, this creates enormous changes on its sensory input. Everything is different. How does it know that, in fact, nothing has changed in the environment? These phi functions allow it to solve the problem without any a priori knowledge of the fact of the existence of space or knowledge of its own body, without calibration of any kind. The second question is the notion of path. We all know that if I go from A to B, I can take multiple paths from A to B, and I know that by adding up these the vectors together, I will end up at the same place. Let's see if the agent can do the same thing. So we essentially tested the agent going from an origin to a destination, taking multiple paths, and we checked to what extent, using the phi functions, the agent was able to say, yes, I'm at the same place I was before, or not. And again, we have very good detection of the endpoint. The detection decreases a little bit when it makes long or paths with many segments, which is what happens with humans. So it's got a good notion of path. And the third test is a notion of displacement. A very important thing about space is that if I take an apple and I move it 10 centimeters to the right, I can understand the notion of displacement independently of the fact that it's an apple. I can take a banana and move it by the same distance, or a pear, or whatever I like. And the notion that I can displace something independently of what I'm displacing is a fundamental notion of space. But seen from within the skull of the agent, where all it has is these numbers, the sensory input that it gets when an apple moves through 10 centimeters and when a banana moves through 10 centimeters, these are completely different. It is just not obvious how to extract displacement from the massive confusion in all those numbers. But using the phi functions, it's possible to extract the notion of displacement. And in fact, this notion emerges automatically from studying the sensorimotor contingencies. No a priori search for the notion of displacement is necessary. And so what we do in this test, this third test, is we take one pattern and displace it by a certain amount, and then we replace the pattern by, say, a square or triangle or some star-shaped thing, and we see the probability of correctly judging that the displacement is the same, and the agent performs very well. So in summary, on space, using sensorimotor contingencies, we can show that a naive agent can extract the notion of space as a vessel by studying sensorimotor contingencies and creating these functions phi. The underlying idea is the idea of rigid motions. And these rigid motions are independent of the agent and the environment properties and the sensory and motor codes. This will work no matter what the agent is, no matter how the motors are constructed or calibrated, and no matter what the sensors are, echolocation, whatever you like. What's important in all this, it shows the intimate link of the notion of space with action. There can be no notion of space unless the agent can act. Action is the underlying cause of our understanding of the notion of space. Sensory-motor dependencies are essential to understand space. Without the ability to act, there would be no notion of space. So I've told you some of the predictions of sensory-motor approach. I've just finished on space. So let's go back to the question I asked at the beginning. Will robots really have emotions one day? Now, I've been telling you about feel. I think feel is really at the basis of all sensations. I think that when you ask about emotions, emotions are more complex kinds of feels that involve visceral reactions. Your heart starts pounding, your digestive system changes. But I think ultimately we can explain emotions in terms of feel. Once we've explained feel, then we can explain everything. So the sensory-motor approach suggests that we can explain feel if we take the new idea that feel is a way of interacting with the environment. This way of thinking about feel has allowed us to explain how feels differ between themselves and how they have a thing that we call sensory presence. But there's something missing. Because you could imagine a robot, I mean, say a bulldozer or a thermostat that interacts with its environment. And it interacts following the laws of sensory-motor dependency. Yet you would never say that a bulldozer feels anything. You need something more. You need some kind of higher level cognitive access to the fact that the agent is involved in interacting with the world. But I think this attending or cognitively accessing, and even you need a notion of self. These things, I think, are the easy part of consciousness. The philosophers consider that there's no logical objection to making machines or artificial intelligence devices that have this kind of cognitive notion. So I'm going to leave that to you, dealing with this higher level cognitive access. But once you have the higher level cognitive access that is sufficiently advanced, then all you need in order to have feel is just interactions with the world. So I think, will robots really have emotions one day? Yes, once they have cognitive access, then we can make emotions. And yes, I think this is coming in the next 20 years. And if you're interested in this approach, you can read more about it in my book, which came out with Oxford University Press in 2011. Thank you.